Hello and welcome, class. My name is Dr. Billman, and I am going to be your instructor for this general chemistry course. So the way that I am going to be breaking this down, the structuring, is, as you can first of all see, that my lecture slides are present. I'm basically walking through my PowerPoints. And by walking through, I mean I am recording my lectures as I normally give them. If you were to sit in my class, this is what you would get. The only difference is that instead of being in person, this is online. This is on the internet. Okay, so the reason why I'm doing this is twofold. First, I am recording this, if you can see the date, in the 2020 COVID-19 pandemic. So this is in preparation for, ideally we'd be in person the entire semester, but COVID's contagious, there will be mistakes, people will get infected, and we will either have to go into quarantine 2 weeks at a time, or we're just going to be shut down, which is the worst case scenario. But if people are taking the pandemic seriously, hopefully we'll be able to stay in person for longer rather than not. And that'll give me the chance then to talk about how awesome chemistry is in person instead of you having to watch these videos online. All right, so the second reason though why I am recording these lectures, thinking more long term, is even once COVID is finished, I will have students, as I have always had students, who are in athletics, who are on the debate team, who end up getting sick, they end up having to miss class. And so in the past, those types of students who have missed class have gotten notes from friends, read the textbook, caught up, but inevitably they 9 times out of 10 still come to my office and I need to reiterate what the entire lecture was anyway, just because they missed that context, right? And I'm sure if you are watching this video, you've missed class once or twice in your life, and when you miss class, it's you may get notes from a friend, but you're ultimately missing the context of what was talked about. And so in my opinion, recording these lectures also has an incredible long-term benefit, because if you are that student who needs to miss class, here you go. If you missed my lecture on the classification of matter, then here it is. You can just rewatch or watch for the first time or whatever, the whole lecture. And I guess there's also a third benefit, which is even if you were in class, if you missed something or you want to watch the lecture again, here it is. So you can use it for studying purposes during the semester, whatever the semester is. All right, so those are kind of my disclaimers. I am recording lectures because it's beneficial to have a backlog for my lectures. All right, so hopefully we won't need to rely on these too much, but they are here and optional. I mean, coming to class in person is always the best. It's the most fun. It's the most entertaining. At least I try to make my classes entertaining. But sometimes we can't, and sometimes it's not safe to, so here we go. All right, so the organization, though, of my semester, as we can see, we're starting with Chapter 1. This lecture series is going to be more podcast style. You can see that there's no webcam. I am just going to be circling things on my lecture slides and stuff. This is also I talk with my hands, I talk with pens, I talk mechanically. And this is normally also how I do it in class. I don't just point to the slides. I actually have a stylus, and the computer screen is a tablet, and I'll write all over my slides. So this is how I normally do it. The only difference again is you can't see my face, but my face is not important. The content that I'm talking about is. All right, so back to what I was saying. The organization is that chapters 1 through 4-ish, I'll say 1 through 4, are all about atoms. So in this chemistry course, we have the semester organized by atoms first, right? We're starting with the very, very small, giving you those basic definitions, those basic tenets, what an atom is, what it's made of. After that, chapters 5 through 7, we talk about molecules, right? So after the discussion of the construction of the atom, we use atoms to build molecules. We talk about how their properties change, how molecules interact with one another, what their shapes are, how they behave, all of that kind of stuff, what the bonding is, how we can describe their construction. And then finally in chapters 8 through 10 is when we get to reactions. So when you think of chemistry, a classic chemistry class, you think of fire and explosions, but we don't actually get in two chemical reactions in this class all the way until chapter 8. The reason why is if you really want to understand what a chemical reaction is and why it happens, you need to know what is going into the reaction and understand the properties of those things going into the reaction. And that way you kind of have like a better grounding for what a chemical reaction is. So we're starting with the very, very small, chapters 1 through 4, right? So we're kind of in quote unquote unit 1 right now. The textbook that all of these lectures are based off of, because if you're here for my class, welcome. If you are here just because, right, if you stumbled upon this video, or like last spring I was uploading some lectures for Chem 202, the spring semester, and I actually got some like messages from like parents who were homeschooling their students, like high school and college, like students who had to go home. And so like if you're one of those, welcome. Also be aware that this is more geared towards like undergraduate college level work, but it is a general chemistry course, and I am starting with the most rudimentary foundational kind of definition. So if you're watching this for high school, it may be like a little above the standards of your high school, but like you should also be able to get it. Prerequisites include being able to do basic algebra. So that's the foundation that we're building off of. If you can do algebra, you can understand the semester of general chemistry. All right, so if you are with me or not with me, the textbook that I am using like to organize and kind of like anytime I have page numbers like this or suggested problems throughout my lecture, the textbook that I'm using is Chemistry, Atoms First, by Burge and Overby. So this textbook, as most textbooks are, can get to be pretty expensive. However, if you wish to like buy an older edition, like these lecture slides are actually all based off of the 3rd edition textbook. So the pages now in the 4th edition, which is what I'm actually using in my class, may be slightly off, but everything should be pretty close. Having said that, the older editions are now much cheaper, right? So 3rd edition is cheap, the 2nd and 1st editions are super cheap. I think like the last I looked, you can actually buy a 2nd edition version of this textbook on Amazon for like 20-30 bucks. So if you would like to get a textbook to kind of go along with it, or just to have a textbook to read chemistry, if you're like studying independently, Burge and Overby is pretty good, and there are some others out there as well. So shop around, see whatever works best for you. But the organization of the other textbooks obviously will not quite match what the ordering is, or the page numbers, or the suggested problems for like what I'm going through here. All right, so without further ado, that's what I'm doing, why I'm doing it. Again, this is going to be very like podcast kind of style. I'm here in my office at home talking into a microphone. Maybe I have some like lo-fi beats in the background on occasion. But what we're really here to do is talk about chemistry, right? Chemistry is awesome. I love chemistry. I'm excited to share chemistry with anyone who's listening. So let's talk about what matter is. So chapter 1 is all foundational concepts, foundational terms, foundational like language, nomenclature, definitions, blah, blah, blah. So what we're going to do is first talk about the way that we classify matter. How do we talk about matter? What is matter and what is chemistry? All right, so let's actually shift into lecture mode. No more pre-lecture content, no more tangents. There will still be tangents as we move forward, but no more pre-lecture tangents. You know, we're actually gonna get going. All right, so what is chemistry? Chemistry, its bare bones definition we can see here is the study of the composition, structure, and properties of matter. All right, so matter is the stuff of the universe. It is what everything is made of, from the sky to power cords outside to the table that you may be sitting at, the computer that you're watching this or listening to this on. Everything is made of stuff, and what chemistry is the study of that stuff. So everything is made of chemicals. If you can think of it, if it is a physical object, it is made of chemicals. Everything is chemicals. Now, chemistry, in my experience, and the term chemical tends to, at least in our culture here in America, have a pretty bad reputation, right? If you hear the word chemical, it tends to be synonymous with dangerous or hazardous. So much so that if we go into the grocery store, they're like, I mean, aside from like produce and legal reasons, there's also kind of like this general subtext. If you're looking at something that's all natural or organic, it's better because it's chemical free. or it's made with like non-GMOs, it's non-dangerous, blah blah. But like everything is made of chemicals, and fundamentally, one banana, an all-natural banana versus an organic banana versus a non-organic banana, whatever, they're all made of the same things. All depending on what banana you're looking at, the proportions may be different, but they're all still made of the same things. And we don't normally see an ingredients list for all natural things, fruits, veggies, whatever, but we can still break down what this stuff is made of. It's made of matter, and the matter that it is made of has names. So the primary ingredient in a banana is water, to be expected. Like, living organisms on this planet tend to have a lot of water inside of them. The second list of the primary ingredients, we have sugars like glucose, fructose, sucrose, etc. And then we start getting into the lesser ingredients. And some of these names may be familiar, like omega-3 fatty acid, but some of these names may not be familiar, like 2-methyl-butyl ethanoate. Down here at the very bottom, if we're looking at here, flavors and colorings. And that name may be a little scary, it may be a little unfamiliar, but at the end of the day, it is a chemical. And even though the name is scary, if you understand the language of chemistry, it actually becomes not scary at all, it becomes informative. The reason why some of these names are a little bit more complicated, like the 2-methyl-butyl ethanoate, I'm just gonna rewrite it over here, 2-methyl-butyl ethanoate, is because in the like organic nomenclature, each of the pieces of this name means something. So 2-methyl, what this means is that there is a CH3 somewhere inside of this molecule. The butyl piece means that we have a chain of 4 different carbons, but with a bunch of hydrogens kind of all stuck together like so. We have a number of hydrogens kind of hanging off of these things, hydrogens, hydrogens, hydrogens. And the ethanoate piece means that we have a carbon, double bond oxygen, single bond to another oxygen, single bond to another carbon. And if we connect these pieces together, which just kind of like drawing lines between them like this wouldn't necessarily give us the correct structure. The ordering of the names, methyl, butyl, ethanoate inside of the term up on top also tells us how these pieces connect together. So ethanoate, again, we have a carbon with a double bond to an oxygen, single bond to another oxygen. We're going to have these 2 carbons here, and this carbon on the end, if I'm remembering my organic chemistry correctly, organic chemists don't come at me, there is a hydrogen, or 3 different hydrogens off of this first carbon. The butyl being right before the ethanoate means that on this other side of the oxygen, that's where this piece is gonna go. So it's gonna go over here. We're gonna say carbon, 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 carbon. Now this 2-methyl piece, it comes before the butyl, meaning that the methyl group, this CH3, is off of the second carbon in this chain. So here's our first carbon, here's our second carbon, here's our CH3 group right here. And now each of these carbons in the chain are also going to have a number of hydrogens bonded to them. So I'm adding some H2s, H2s, H3s, but this is what the molecule 2-methyl-butyl ethanoate looks like. And so now from the name, we have a picture for what the molecule looks like. And again, this is kind of out of context. You're like, yeah, well, that doesn't mean that the chemical's not bad for me. This in the, is listed in the colors and flavors section for a reason. This is one of the chemical compounds that gives you that kind of classic banana flavor. So if you think of like Runts candies, or even if you're like eating a banana, this molecule is a piece of that like classic banana flavoring. And now suddenly it's familiar. You understand what it means, and that flavoring, that scent, has a chemical composition as well. This is what the molecule looks like right here, and this is what the chemical name is. So now you know what to call it. Instead of just being generic banana flavor, you now know that the chemical name is 2-methyl-butyl ethanoate. And yeah, you're not gonna throw that around in like everyday conversation, but you could. All right, so that's the kind of stuff that we're gonna be looking at in this class, right? That's what I wanna break down. Even if the only lesson you get from my class is stuff is made of chemicals and that's not bad, like my job is done. So let's talk about what the rest of that stuff of the universe is, because right, our conversation doesn't just end with bananas, it's everything. So the stuff of the universe can be broken down into one of two pieces, one or two camps. The first camp is matter. Matter, by definition, has mass. It has heft to it. It has weight. And the second requirement for something to be classified as matter is that it has to occupy space. It has to take up physical space in like our three-dimensional world. You know, like a lamp or a cup or a book. These are things that have mass and they take up space. All right, if an object either has mass but does not occupy space, or if it occupies space but does not have mass, or if it doesn't do either of these, then it's energy. Energy tends to be thought of, because it's like really esoteric, but like one way that we can try and think of it is it's like the way that stuff interacts with each other, right? So if one thing is hot, another thing is cold, energy will flow from the hot thing to the cool thing. So energy, like by technical definition, is the quote-unquote capacity to do work, but really we can think of energy as the way that matter interacts with each other. All right, so in the illustration that I have here to the right, because yes, I do love to address the figures that I have on my slides, for anyone who has ever seen Bill Nye the Science Guy. First of all, Bill Nye's rad. He's one of the reasons that I became a scientist. His show was on TV on PBS when I was growing up. It was my favorite thing to watch after school, because Bill was able to answer the questions that I had for my parents that they weren't able to answer. Things like, why is the sky blue? Stuff like that. And Bill Nye had those answers, and I was like, oh, science is really cool. Like, science is the study, like, it's trying to understand the world around us. And so in this particular episode, the man who is the narrator, who oftentimes in the show will talk to Bill, if you've never seen the show before, it breaks the fourth wall a lot. The man who is the narrator says, what's the matter, Bill? And Bill, you can see in the next panel, is like, everything. Everything is matter. Except energy, of course. And so this, to me, really kind of exemplifies, again, like, not only can like the universe be broken down into these two camps, matter or energy, but you can also have a fun pun surrounding that. So everything is matter, and if it's not matter, it's energy. All right, so we will talk about energy and how matter interacts with itself, with each other, later in the semester. So that's going to be more like chapters 8, 9, 10, chemical reactivity, chemical reactions kind of stuff. We are going to be starting again with the building blocks. So in the category of the stuff of the universe, we are going to be first focusing on matter. And of this matter, we can break this down even further, right? Because we're defining things technically today. That's what this first lecture is. Matter can be broken down either into atoms or molecules. So an atom is a physical thing. It is a near infinitesimally or infinitely small building block of the universe. It is near infinitely small, again, to emphasize the fact that it is super, super tiny. Now, atoms, when they combine together, form molecules. So a molecule, by definition, this is a collection of atoms. They're chemically bound together in some type of characteristic pattern and proportion. So an atom, super infinitely small. This is what we're going to be talking about in chapters, this chapter, but also 2 through 3. So we're going to be really breaking down even more so than just defining it's really small, like what is an atom? Atoms are made up of subatomic particles. Put them together, this is our building block. So we can think of atoms in more of a like classic sense as a Lego. These are the building blocks that when you put them together, as we can see kind of illustrated on the right, where each of these little like spheres inside of our structure is an atom. So that's an atom. And that's an atom. And that's an atom. Each of these pieces are atoms, and each of the lines connecting the atom is going to be representative of a chemical bond. And we can see that there are certain atoms, like these red atoms here, all have 2 bonds coming off of them. So this red atom has 1, 2 bonds. The red atom over here has 1, 2 bonds. Each of these red atoms, like this one here, has 1, 2 bonds. versus the black atoms all have 4 bonds. So each of the black pieces, if you were to look at them, they all have 4 of the bonds sticking out, and each of these small white ones all have 1 little line sticking out. And this is actually to be expected. It's not just coincidental to this hypothetical molecule, which we have illustrated here, which, fun fact, is fructose. So this is a sugar molecule that comes from fruit. But each of the, like the red, the black, the white, correspond to oxygen, carbon, and hydrogen respectively. And so each of these atoms has a very characteristic expected type of bonding pattern. And so if we recognize the patterns, if we recognize the proportions, we can start to predict how atoms come together to form molecules, which again is where we're going with this whole semester. All right, so how do we classify those pieces of matter? So when I say that, what I mean is what we've just finished defining, atoms and molecules, to use more of a humanities kind of term to kind of explain where I'm going with this. Atoms and molecules we can think of as nouns. They are physical things. How do we break down and describe these physical things? What are the adjectives that we use to be able to define what type of atom we are looking at or what type of molecule we are looking at? Well, that is what the terms to the left that I've bracketed kind of tell us. Are we working with something that is a pure substance? So the adjectives that we're going to use will be element and compound. Or are they mixtures, where the adjectives we're using will be homogeneous mixture or heterogeneous mixture? So based off of kind of basic observations, we can either make a prediction or a hypothesis about what the classification or how we can describe matter is. So for instance, if we look at the illustration here on the right, it looks like we have these really nice, right, if we just record our observations, because in science, if you don't write it down, you're just screwing around, to butcher a quote from Jamie in Mythbusters. Jamie or Adam? Adam Savage. Regardless, let's write down some observations that we have of these kind of silverish, shiny cylinders. Well, they are shiny. They are silver in color. They are cylinders, and this may seem like a silly fact to write down, a silly observation, but it does actually tell us something about the matter, because do cylinders naturally occur out in the wild? Like if you were to see this sitting out in the wild, would you assume that it was just a part of nature, or would you assume that it was man-made? Probably man-made. So the fact that it is in the shape of a cylinder does tell us something about the matter that we are observing. It tells us that it's been purified. So if this more than likely is an object that is man-made, and it looks like it is a pure form of some type of metal, chances are it's going to be a pure substance. All right, so this helps us to further, just based off of observation, kind of break down and classify what type of matter we are working with. Now, there is more than one atom here. We can conclude that because it's an object we can see. Either there are multiple atoms or multiple molecules that have been pushed together or crunched together to form this type of shiny silver cylinder. So either we're going to be working with pure, one pure element, something like silver, or we will be working with multiple elements, giving us something like stainless steel, possibly. All right, so if we're working with something that is just one element type versus multiple element types, we can start to see that this is going to be where the breakdown between element and compound is. So let's more technically define element and compound. Put a pin in mixtures, we'll talk about mixtures, but let's just focus on pure substances first. So thinking of these shiny silver cylinders, how can we break down or categorize element versus compound? Well, if we're focusing on elements first, right, because we're just gonna take this one bite at a time, one step at a time, an element is a type of matter that consists of a single element type in fixed proportions. All right, so what elements are we working with? Well, fortunately for us, there is a beautiful handy-dandy table known as the periodic table, which has a list in graphical form of every single element that we know of. There are currently on the periodic table 118 elements. And so if we are working with a chunk of pure substance that is categorized as an element or can be classified as an element, it means that every single atom inside of that thing, like we can see over here, is all made up of one element type. So if we're observing a diamond, for example, each atom, if we were to zoom in on this structure, what we would see is one carbon bound to another carbon, bound to another carbon, bound to another carbon, bound to another carbon, bound to another carbon. You see where I'm going with this. Each of the atoms inside of this structure, which I am not drawing like the structure of diamond, if we were to actually like decompose this structure, but like this is for all intents and purposes what I'm trying to demonstrate, that each of these spheres that you would see, if we could hypothetically zoom in to the point where we could see atoms, you would see each of these atoms being the exact same. They would all be carbon. And so each of these carbon atoms, when stacked up, when you have enough of them all together, forms an object that we can physically see, the type of matter that we call a diamond. All right, so on the periodic table, we have, again, 118 elements to choose from, and the element that we would say that diamond is made of is known as carbon. So the periodic table square that has carbon on it, we can see the element name tends to be on the top of the square on the periodic table, and the rest of the information that is present may vary in terms of how much detail there is, but bare minimum, the periodic table tends to at the very least contain the element's name, what its atomic number is, so each element has a number associated with it. Carbon's is 6, and again there are a total of 118. Each element has a symbol. Carbon's is a big ol' capital C. Most of the elements' symbols tend to be like either the first letter or the first two letters inside of the element's name. This is not universally true, but for most of the elements on the table it is. And last but not least, the information that tends to be present is how much that atom is going to weigh. So if we had a scale that was sensitive enough just on the per atom basis, carbon, we would expect to weigh on average 12.011 atomic mass units, or AMUs. So AMU is atomic mass unit. Atomic mass unit, AMU. All right, so this is what an element is, right? Again, it is a chunk of matter. It is a hunk of physical stuff that is all comprised of the same element type in some type of fixed repeating pattern, fixed repeating proportions. So how is an element different from a compound? Well, a compound is matter, so again, it's like a physical thing that consists of two or more elements in fixed proportions. So here's the big difference, the two or more elements. Something that can be classified as an element only has one element type in repeat throughout the entire object. Something that is classified as a compound is going to have two or more elements in fixed proportions, and not only that, but they tend to be chemically bonded together. So if we're looking at a glass of water, water is kind of commonly known and jokingly referred to, even by people who don't really know chemistry comprehensively, as H2O. And that is because if you break down water, which we call H2O, it's because it's made up of hydrogen, which is our H, and oxygen, which is our O. And the chemical composition, like the actual construction of the molecule itself, our compound, we can see is on the right over here. We have our one oxygen in the middle, we have a hydrogen on the left, and a hydrogen on the right. So the oxygen and the hydrogen are two different element types on the periodic table. Oxygen is an element, and hydrogen is a different element. So here we have met that condition. We have two different element types. They are, we can see, bound together. The elements are kind of smooshed together. This means that we are working with elements that are chemically bound. So we have now a molecule, and this molecule is a type of compound known as H2O, or water. And if we get enough of these molecules and put them all together, what we end up then is with a chunk of stuff that we can see, or a chunk of stuff that is going to be flowing inside of a glass, that we would refer to as a collection of H2O. All right, so a glass of water, we would tend to classify this, if it is just pure water, right, distilled water, as a compound. All right, so this distinction between elements and compounds, before we talk about mixtures, we can also address a little bit more the distinction between elements and compounds, since this is really sort of where, like, our understanding way back in the day of chemicals and what their construction are started, right? Humans have always been very interested in categorizing things and being able to break things down in order to understand the world around us. And so back in the late 1700s, a man by the name of Joseph Louis Proust was the man not just to discover, because science is a collaborative process, there were multiple people kind of working on this, but he is the man attributed for kind of concisely stating what we now refer to as the law of constant composition. Now, what this law is, first of all, scientific laws are consistent and universal, true observations. Right, so no matter where you look in the universe, this statement will be a true observation that could be made about the thing that is being observed. So the elemental composition of a compound, by definition, is always combined, or the elemental composition of a compound, is always combined in the same proportions. My brain kind of like tripped a little bit. So what this means, to give like a little bit more of an example, is water, for example, as a compound, is always 2 hydrogens and a single oxygen. If the molecule has 2 hydrogens and 1 oxygen, it is water. These are statements that are in both the forwards direction and the reverse direction true. It is absolutely true. And no matter where you look in the universe, this definition will be constant. If you look at water, or a molecule, let's say, like on the other side of the universe, and it's made up of 2 hydrogens and 1 oxygen, it's gonna be water. So this is true no matter where you look. The other caveat of this is, let's say we're looking at a molecule that is made up of 2 hydrogens and 2 oxygens, right? But like, it's only one element different. Like, how much different could that compound be? Well, the compound with the formula H2O2, right, so different than water, is known as hydrogen peroxide. And hydrogen peroxide, if you've ever come into contact with it, because it's still commonly used as like a sanitizer, a disinfectant to like clean wounds and stuff, if you've ever had this like poured onto a wound, you know exactly how different hydrogen peroxide is than water. One element, one additional oxygen, makes a huge difference in terms of what the like chemical properties for what the compound is going to be. So this is really the importance of the law of constant composition. Not only did Joseph Louis Proust like insinuate with this law finally being recorded, is that like a compound that is known or can be recorded as like H2O is going to be water, but if there's not 2 hydrogens and 1 oxygen, it's not water. And this is true again for like all forms of matter. If you have the wrong number of elements inside of your compound, it's going to be a different compound. All right, so continuing with our discussion of pure substances, not only can we kind of break down the consistent composition of these compounds based on the elements that go inside, but we can also start kind of breaking down the nomenclature that we use for referring to these elements and compounds. So I've thrown around H2O for water, and what's important to recognize is that this is known colloquially, right, as a chemical formula. And a chemical formula, by technical definition, is a combination of elemental symbols. So like our H and our O, these are the elemental symbols and numeric subscripts, where the subscript you can see, that too, when combined, represent the chemical composition of that substance. So H2O, all of the subscripts immediately follow the element that there is that many of. So in H2O, what this tells us is that there are 2 hydrogens and 1 single oxygen, right? I can't write red on red, so I'm gonna kind of like offshoot it. But this big guy is oxygen. All right, but this is true. This structure, this formatting, we can use not just for compounds, but also for elements. There are some elements where there is like a specific number of atoms that is required in order to meet the like known chemical properties of that particular elemental substance. For instance, if you have a collection of 60 carbons, you could have graphite, you could have diamond, or you could have this fun thing. Now, this funny looking thing is known as Buckminster fullerene, or a buckyball for short. It is a real element. It is a real molecule. Note that molecules can be made of elements, just one element in repetition. This Buckminster fullerene molecule organizes, like the number of carbons, 60 of them, organize into the shape of a soccer ball, which is super strange. We did not make this, right? We might think that this looks man-made, but this is a naturally occurring element, a naturally occurring molecule that was found out in the wild. It is naturally found in kind of like a gaseous or dusty form above the surface of graphite, so like pencil lead. And each of these carbons, we can see, kind of arranges itself in the vertex, or into a vertex where, like, when you put them all together, we have a bunch of hexagons, pentagons, hexagons, pentagons, in kind of an alternating form, which when combined turns into a soccer ball. It's crazy, it's awesome, it's coincidental, but that's sometimes how science goes, right? Life imitates art. All right, so we can use these chemical formula to shorthand represent what the either atoms, molecules, compounds, elements, like what it is that we're working with, right? Buckminster fullerene is a very long word. C60 is very short, and so it's going to be much nicer in order, just for conciseness, to like represent the things that we're working with their chemical formulas. All right, the textbook that we're going to be using, or any textbook that you could be using, will also include visual models of these pure substances, again, whether they be elements or compounds, whether they be atoms or molecules. So the 3 different forms of these visual models we're just gonna break down, talk about the pros and cons of each. The first we have illustrated here is known as the structural formula. So the structural formula, by definition, lists out specifically what elements are present and what bonds are present between each of those elements. So we can see specifically how the bonding works, which elements are connected. It's really good for clarity. Structural formulas are probably like the most common form of illustrating molecules. In fact, as we continue throughout the semester, we're going to learn how to draw these ourselves. But for as like explicitly clear as to which elements are present and what bonds are present, the downside, the con of using the structural formula is that it doesn't illustrate 3D geometry very well, right? It is literally a 2D picture. And you might like ask yourself, like, well, how different could this look in 3D? Well, to answer that question, all we need to do is look at the other 2 molecules that are illustrated here, because each of these visual models are depicting the exact same molecule, ethanol. So the first structure that we can see explicitly, there are carbons, we have an oxygen present, a bunch of hydrogens present, but it doesn't give us the any good feel for how it's going to look in 3D. So that's what each of these other 2 visual models do. They represent our molecule in 3D. The distinction between these 2 3D versions The first, the ball and stick model, which is over here on the right, we can see also looks visually different than the space filling model, which is the third one down. Now the ball and stick model, its advantage, again, kind of similar to the structural formula, is that we can see the bonds clearly. So we can see that there's a bond here, we can see that there's a bond here. So we can kind of pick out, again, assuming that the atoms inside of this molecule are consistently color-coded, we can see that there's a carbon bound to a carbon, which is bound to an oxygen, bound to a hydrogen, which kind of matches what we see in the structural formula up above, right? Carbon bound to oxygen, bound to hydrogen. It's just now we can see what that construction looks like in 3D space. The con of the ball and stick model, though, which is another con of the structural formula. It's just, it's not the type of con you think of because the atoms aren't illustrated as atoms in the structural formula. But the con of the ball and stick model is that nothing is to scale, right? Each of these atoms is represented by a sphere with the exact same diameter. So we don't get any real feel for how big each of these atoms is because we're so focused on being able to see the bonds between the atoms. This is what the kind of distinction is then between ball and stick and space filling. In the space filling model, atoms are I'm just going to use the same terminology. The atoms are all to scale relative to each other. So we can see how much bigger the carbon atom is when compared to the hydrogen atom. We can see that this carbon is kind of filling up this whole space here. The other carbon is kind of mushing into it. This whole thing ends up looking like an overinflated balloon animal. It's very large and very smooshed together. So that kind of leads us to the con of the space filling model. It can become a little bit difficult to see exactly what is bonded to what, particularly in molecules of larger size. It can get to be a little bit strange to look at. But the advantage is that we can really see what is the chemical bond. A chemical bond is caused by the overlap of two atoms, the overlapping of the atomic orbitals. We'll be talking more in detail about that later. So for instance, this oxygen and this hydrogen we can see are smooshed together, and this overlap right here is the chemical bond being illustrated. It's just difficult to look at because we classically think of a bond as being a line. It's not actually a line. All right, so the disadvantage of our space filling model is that it's hard to see exactly where all of the atoms are. It's hard to kind of pick out how they connect, but it does give us a more accurate version of what the molecule looks like, quote unquote, looks like in 3D. All right, so as you're reading through your either textbook or handouts or whatever the situation is, if you're in my class again or a different class, welcome to all. I'm just here to spread the joy of chemistry. You're going to be seeing these 3 different forms of visual models. So just kind of know that you can, there's pros and cons to each of them, all depending on how explicitly clear you want to be about what elements are present versus how it looks in 3D versus what the bonds and connectivity are, etc. All right, so that's pure substances. Pure substances, again, atoms and or molecules made up of elements and or compounds. So what's a mixture then, right? Because if we already have either one element present or 2 or more elements present, what's a mixture then? Well, a mixture consists of 2 or more pure substances, not present necessarily in any fixed proportion. So we used elements, or we defined an element and used that to define what an atom could be. We then also use that to define a combination of elements as a pure substance, known as a compound. Here now we are mixing multiple pure substances together. So we're kind of increasing size or increasing magnitude a little bit. And again, note that the combination of these pure substances is not necessarily in any type of fixed proportion. So to get an idea for what mixtures could be referring to, we're going to give an example, but also at the same time compare and contrast the following 2 definitions for, first, a homogeneous mixture, and second, a heterogeneous mixture. All right, so a homogeneous or homogeneous, all depending on how you pronounce it, both are totally accurate. I hear it both ways all the time. So I tend to fall onto homogeneous just because I think of homogenized milk. A homogeneous mixture is a composition, or is combined. It is a composition of a physical mixture that is consistent throughout. So what I mean by this is we have two or more pure substances that are physically mixed together. So they're not necessarily chemically bound, they're just physically in the same space as one another. And the mixture is even. So we can think of a physical example of this type of mixture of multiple substances, particularly a homogeneous mixture, as a glass of homogenized milk, right? Homogeneous mixture made up of two or more pure substances. Homogenized milk is a really great example of this, because inside of milk we have things like water, fat, salt, lactase, etc., like all of the things that go into milk. But if the milk is homogenized, we don't really pick out like, yes, this drink in particular was a little bit more watery and this drink in particular was a little bit more fatty. Like, that's gross. Like, we homogenize our milk, we evenly mix it throughout so that one drink is exactly like the next. Everything is evenly spread. Everything is thoroughly mixed. That's what it means to be a homogeneous mixture. Now, a heterogeneous or heterogeneous, again, I hear it pronounced both ways, heterogeneous and heterogeneous. In kind of contrast from that, we do have, again, a mixture of two or more pure substances, but this physical mixture is not consistent. It is not evenly mixed. We have chunks present. So this heterogeneous mixture, a really great example, is like chunky peanut butter. Right, we can see there are visual chunks, pockets of space where there is one physical or one like type of substance that's not present immediately right next door. Right, we have creamy peanut butter and we have chunks of peanut. These two things are physically mixed together, but the result is that one bite is not exactly like the next. Right, so one scoop could have more peanuts, one scoop could have more butter. If you're buying the like quote unquote all natural peanut butter and you let it sit for a while, then you actually also see like the oils separating out from the butter and you have to like stir it up to try and make it like more of an even mixture. That is a good example of a heterogeneous mixture. All right, so homogeneous and heterogeneous, these two examples are more like macroscopic scale, but we can also trace down homogeneous and heterogeneous mixtures down to the molecular scale. Right, we find, based off of observation, that a lot of these like macroscopic observations that we make on materials can actually be like traced back to exactly what their like chemical like depiction is. In other words, if something appears macroscopically like a homogeneous mixture, it's because if you zoom into the molecules, it's also a homogeneous mixture. So let's draw what the molecular scale depictions of elements, compounds, homogeneous mixtures, and heterogeneous mixtures look like. All right, so our first example for an element, let's just draw O2. So there, in O2, O2 being there are two oxygen atoms present, right? The subscript following the element means that we have two of that element inside of what the molecule is. So the molecule is going to be made up of two different oxygen atoms kind of bound together like so. And if we are looking at a sampling that is a pure substance, a pure element, we're just going to have a bunch of these O2s floating around. Right, so if we were to continue collecting all of these O2s into a vessel and kind of like zoom out or like have a large collection enough that we could like zoom out and just look at a jar, right? A jar of pure O2. What it would look like is just, I mean, first of all, kind of empty, but second of all, that collection of pure substances, as we can see here, then can be traced down just by like looking at a sample bite size of like the whole. All right, the compound, let's just keep going with H2O, right? H2O is a really great example. With the molecular depiction for a collection, right, of substances, again, being defined as a pure substance, a compound, we're gonna have just a collection. I'll even like color these oxygens in. So we have a bunch of these oxygens with little hydrogens sticking off of them. but no matter where you look inside of this vessel, right, if this is just a window, a snapshot, or a zoom in, if you were to like look over here or expand your view, all you would see is water, right? Water for all the eye to see everywhere. The entire vessel would be filled with H2O, which is what defines this collection as a compound. All right, so our distinctions now are going to be in the homogeneous mixture versus heterogeneous mixture. So a homogeneous mixture, again, is going to be an even or equal kind of combination of two different, either two pure substances. It could be two elements, it could be two compounds, it could be an element and a compound. So you know what, let's look at that. Let's look at a homogeneous mixture of O2 and H2O. So a homogeneous mixture is going to be evenly spread throughout. When you're zooming in, again, quote unquote, zooming in this close to observing like individual molecules, there may be kind of the appearance that like your substance is chunky, but again, we're thinking about the combination of these like elements, these compounds, as we kind of like continue building the sample and allow it to like aggregate into something that's more like macroscopic. So like, for instance, a glass of water that has oxygen infused into it would still just look like a glass of water. It just happens to have more oxygen than what would like naturally occur in a glass of water. So what this would look like molecularly, we'd still have all of our water molecules kind of present, hanging out, floating around, sliding past one another as liquids are wont to do. I'll even draw another one up here. But we would also have oxygen present, right? This is a physical mixture. The oxygen is not going to be chemically bound to the water. Instead, it's just going to be hanging out. Kind of evenly mixed throughout. And again, it kind of appears because we are so zoomed in that it's like, oh, well, here's a pocket of oxygen and here's a pocket of oxygen. But it's kind of like an illusion that's caused by, again, us just zooming in so close to the picture. If we were to allow the oxygens and the waters, again, to aggregate and form something that's more like macroscopic that we could actually collect in our hands, there would be more waters like around, more waters present, everything would be moving and like sliding past one another. It would definitely end up being an even mixture of oxygen and water. All right, well, what would a heterogeneous mixture, let's, just for consistency's sake, oxygen and water again. If we were to like freeze the water and force it to separate from the oxygen, what would a heterogeneous mixture of the same like pure substances look like? Well, the difference would be that all of the waters would aggregate together, especially if they're frozen. They're going to be like kind of physically interacting with each other in a solid form, but all of them are going to be segregated or separated from all of the oxygens, which are going to be hanging out up here. So now we can see that not based off of like kind of illusion, but like there is a clear distinctive line between where the waters and the oxygens are. And if we were to continue like adding more and more oxygens, adding more and more waters, and allowing this to aggregate into a aggregate into a like physical substance again that we could hold in our hands, we'd end up with like a jar where there's frozen water on the lower half and what would appear to be just empty space, but it's actually filled with oxygen up on top. All right, so this is the molecular difference between our homogeneous mixture, heterogeneous mixture, and not only that, but a collection of elements and a collection of compounds. All right, so here we come to the first example of an example problem that I have. Normally in my lectures, what I do is when we get to this type of a problem where, for example, if we want to further dissect classifying matter, I have a problem listed here, which is identify the following as an element, compound, homogeneous, or heterogeneous mixture. There are 6 items listed. How I normally handle this in class is I just let students kind of break out and work together. So either on your own or in partnerships or in groups, people can discuss and come up to kind of a concise and conclusive answer. Obviously, we can't be doing that with pre-recorded lectures, so what I'm going to do instead, first, pause the video, see if you can't answer these questions for yourself. Can you identify whether wine, Cl2, sugar, snow, are these elements, compounds, homogeneous mixtures, or heterogeneous mixtures? As you unpause the video then, I am going to kind of talk through, here's how you would classify potentially each of these pieces of matter. Second part is I am also going to like extract this section from the lecture and post it as a separate video. So that way, if in the future you would like to come back and refer to this example problem, you can without having to scrub through the entire lecture to find it. And this is going to be true of every example problem that is going to be present in each of my lectures. I will answer the question in the context of the lecture, but I'm also going to extract it into a separate video, so that way if you want to come back, it's going to be much easier to find. All right, so here's the moment. Pause the video if you're watching, break this down for yourself, is it decompress? Is that the word I'm looking for? Process the information that I have given you so far. See if you can't answer this question on your own before we come back together. All right, assuming that you just paused and unpaused, we are now going to go forward and answer, I will answer the questions, I will define each of these, I will classify these forms of matter as elements, compounds, homogeneous mixtures, heterogeneous mixtures. All right, so the first example here, wine. We're just gonna go through each of these one by one. First is wine. All right, so if you think of a glass of wine, you think of a beverage that you drink. Something akin, again, to like a glass of milk, a glass of water, whatever. You do want, and you would also expect that this piece of wine, this substance of wine, is going to be some type of even mixture. Even because you would expect the components to not chunk up. I mean, if your wine is chunky, it's probably gone bad. You would also assume that wine is going to end up being a mixture. And the reason why is, if you think about, again, the process of making wine, if you are aware of what this process is, you end up like smooshing grapes, right? That's kind of the classic image, is like a bucket of grapes, people stomp all over them. The foot fungus ends up allowing for the fermentation process of the grape juices, which eventually over time creates wine. So we have water, we have grape juice, we have alcohol present. There are multiple facets, multiple pieces that comprise wine, hence it being a mixture. So if we're looking at something that is an even mixture, by definition, this is going to be a homogeneous mixture. Right, so when defining or classifying matter in the world around you, you're gonna have to use either context or previous experience, or kind of look up to see, like, is there an ingredient list for wine? Is it made up of two or more substances? Yes or no? That's gonna help to answer that first question. Is it a mixture or not? And then the second caveat is it going to be even throughout or not? Right, so wine, we would expect to be a homogeneous mixture. Cl2. Cl2, first of all, we can see is present as a chemical formula. Well, you can't write one single concise chemical formula for any type of mixture. And the reason why is that a mixture, again, is two or more pure substances. You would have to write two or more chemical formulas if the substance was a mixture. So right away we know that Cl2 is not a mixture, it is going to be some type of pure substance. Our follow-up question is, how many element types are present? Now Cl2, there are two chlorines, so there are two atoms present inside the molecule, but each of those atoms, each atom is the same element type. Each of the atoms is chlorine. And so because we have a chemical formula, so we're looking at a pure substance, and each of the atoms inside is made up of the same element, we can define Cl2, we can classify this piece of matter as an element. All right, next up, we have air. Air in the world around us, just neutral, natural air. Well, air, we know from past experience, I'm sure you've learned this at some point, is comprised of like 70% nitrogen, it's like 20% oxygen, it's got a bunch of CO2, it's got argon. These are the top four like components of air. And because now here we can see, kind of in contrast to the Cl2 example from before, we have multiple chemical formulas present inside of air. And because we have multiple chemicals present, we would assume that this is going to be some type of mixture. The question is, what type of mixture is it? Well, to answer this, all we have to do is think about our experience with air as we just observe it in the world around us. As we're walking around, we don't have to chase like pockets of oxygen throughout the nitrogen to stay alive, right? We can just sit where we are, and the air is kind of evenly dispersed in the world around us. So because the air is evenly dispersed, thank God it is, we are working with a homogeneous mixture. Like, could you imagine if air was heterogeneous? And I mean, okay, if you zoom out far enough, if you like consider the total atmosphere going out into space, yes, there are distinct layers that form there, but we're not talking about those distinct layers. We're not talking about the atmosphere. We're talking about ambient air around us. All right, next we have stew, right? Just a chunky soup that you can eat. Well, I just said the word chunky. And if there is anything chunky about the substance that you are observing, about the piece of matter you're observing, chances are it's a heterogeneous mixture. Right? It's not chunky in terms of like texture necessarily. It's chunky in the sense that you have like beef broth and like visible chunks of like peas, potatoes, tomatoes, beef. Like, because there are all of these different pieces that have distinct and easily separatable pockets, we are clearly looking at a heterogeneous mixture of multiple things just kind of being physically mixed together. All right, sugar. Honestly, sugar and snow lead to like the best discussions in class, and the reason why is that you can possibly argue multiple answers for these. So sugar first. If we think of just classic sugar, like sugar that you pour into your coffee, sugar that you like eat inside of like cookies or whatever, classic sugar is glucose, which is C6H12O6. And that's it. We have one distinct chemical formula, and this one distinct chemical formula is made up of 3 different element types. And so the most straightforward definition for how we would classify sugar as matter would be a compound. Right, that's the path of least resistance. Occam's razor, easiest answer is probably going to be the answer. We're just looking at a compound here. The reason why sugar has a second answer though, a second option, is not all sugar is glucose. We also have sucrose, there's fructose, like for instance, high fructose corn syrup. And there are sugars that are sold commercially that can just be generically referred to as sugar that are a combination of all of these lesser, or like, I shouldn't say lesser, right, some of the parts. It's a combination of glucose, fructose, all of the different oses that make up sugars. And if we're looking at a combination of these sugars, we are looking at a mixture of some sort. How closely, like, how do I say? All depending on how small the grain of the sugar is and how evenly mixed it is, you could be working with a homogeneous mixture or a heterogeneous mixture, but it would be a mixture nonetheless. All right, so if you're that really, if you're that type of like pedantic person who's like, well, technically, chances are your answer is going to end up being the mixture answer, because a lot of the time, again, sugars, especially if they're sold in syrups like Caro syrup, are going to have multiple sugars present. All right, and similarly, snow is going to have multiple answers. Now, the most generic answer, again, the most straightforward answer, and this is the answer that most students give, well, snow is just frozen water, and frozen water is made of H2O. Just like the sugar example, we have one chemical formula comprised of 2 different elements, meaning that we would define snow as a compound. But again, if you're that type of like pedantic person who, like, you know, in the middle of this conversation, I imagine someone who looks very like Urkel-ish, just like knowingly pushing up their glasses up the bridge of their nose, and they're like, well, actually, If you think about the construction of snow, snow is formed specifically in the upper atmosphere because there is some type of piece of sand, hair, dirt that has been kicked up into the upper atmosphere that allows water to freeze onto. So at the heart of every piece of snow, there is a little like speck of dust, a speck of skin, a speck of something that allowed water to aggregate to it. So if we're thinking of that, if we're thinking of there being this like little seed and the snowflake building up on top of that, we're going to be looking at a heterogeneous mixture. Right, because we could break off all of these ice crystals from this little speck, isolate the speck, it'd be pretty easy to separate that. All right, so I like this example. Kind of starts off easy and straightforward, then it kind of makes you think the further and further you go, because all depending on how you define the type of matter you are working with, you could end up with different classifications. So it's going to be really important to, when you are communicating either with your peers, with me, like exactly what type of matter are you working with? Is it just a generic kind of image of something like wine or air? Or are you going to end up being more technical? What type of sugar? What type of snow? Real or hypothetical are we working with here? All right, so if you are just watching the separate scrub or the separate video, so you don't have to scrub through the entire lecture. Awesome, let's just get back to lecture. If you're watching this in lecture, welcome, you're still here. I'm not gonna give that transition every time, but I do want to just kind of demonstrate again, reiterate the point. If you wanna come back to this example later, it will be found in a separate video, or can be found in a separate video. All right, with that though, our lecture is finished, right? So if I hit next, the next slide is actually what the next lecture is. So normally, or on occasion, I should say, 9 times out of 10, the actual like lecture, to go back a slide, the next slide after this would be like a series of suggested problems. But our textbook, the 3rd edition at least, doesn't really have good like review problems for classifying matter. So I would encourage you to just practice by looking at the world around you. Look at the stuff that is existing in the world around you, right? It's made of chemicals. How would you classify the matter that you're able to like just witness, observing in the world around you? So kind of keep that in the back of your mind, right? Everything is chemicals, and we can classify that matter accordingly. So if you have homework, do your homework. I'm gonna try and keep these lectures also as a note moving forward. I'm gonna try and keep these lectures as like timeless as possible. So I'm not going to say like your homework are these problems specifically, because that might not be true in future years or future semesters, or it might not be true if you're not actually in my class. So again, I'm going to try and keep these as like timeless and generic as possible. This lecture was on the classification of matter. So if you'd like example problems, go out and find some example problems. If you were in my class, double check Blackboard or whatever our like learning service is at the time, because if we change away from Blackboard, that's not going to be true in the future either. Double check what your homework assignment is. But other than that, awesome job today, guys. Class is dismissed.